Anyway, he's going to talking about tracing just-in-time compilation for effects and handlers. I'm going to stop my.
So, hello. First of all, this is joint work with CF Bolz and Jonathan Brachthäuser, who's also here. So the motivation for this work is that effect handlers can express all kinds of programming language features like event-based programming, asynchronous programming, and so on. So that's really nice. But if we implement them naively, then there's a performance cost. And we don't want that. So there have been various approaches to getting that handled. And at first, there are ahead of time optimization approaches. For example, with rewrite rules by Karachalias and Bretner and Zichkovsky, or by a CPS translation with like what Philip Schuster did, and also Marius Müller. Then there are approaches that implement efficient runtime systems, like the Alvarez-Picalo one, Kong Ma recently, and also Casey's work on retrofitting it into OCaml. What we haven't seen yet is any approaches doing just-in-time optimization. And this work tries to fill that gap by exploring tracing just-in-time compilation for effect handlers. For this, we formulated multiple research questions. First, we want to know how does an approach using tracing just-in-time compilation in this case compare to the already existing ahead-of-time work. Then the question is which classes of programs with effect handlers can this approach optimize well, and where it is limited and doesn't work so well. Also, we are interested in optimizing that performance even further, so what can we kind of wiggle on to get this faster. And for differences between different kinds of effect handlers that we might implement. And finally, also, how does this affect performance for programs that do not use effect handlers, because we want to write those too. In this talk, I'm going to just focus on the first two questions. For the other ones, you'll have to look into the paper. Now, our implementation approach starts off from 3 languages with effect handlers. First, EFF, the original language with effect handlers that uses dynamic effect handlers. Then the language developed in our group, which is Effect, using lexical effect handlers. And finally, Coca, which has both dynamic and named effect handlers. And we translate those 3 languages via a common IR to our own bytecode format that supports delimited control operators, and then run those on a tracing JIT implemented using RPython, so maybe best known for PyPy. If you don't know what a tracing JIT is, the general idea is we trace the execution flow of hot parts of the program and then optimize and compile those straight line traces. Let's look at an example. If I have this program using effect handlers, there's first a push stream producer, and it has an effect handler call or an operation call here in the emit. Then there's a consumer that's also a producer, which has an effect handler here with the try with. And finally, another push stream consumer. And we combine those to count some nonsense number of emitted values. And if we execute that, then we might push operations on the stack, which is here at runtime. And at some point, we'll reach one of those effect handlers. Whenever we do that in our implementation, we put a marker on the stack and kind of make 2 stack segments out of it. So this looks like this. We have a new stack segment that we'll push on. And then we just continue. So go into the body. We might install another prompt for another handler. And at some point, we reach this code. And if you've read that in more detail, then you'll notice this is basically a loop. So we execute some iterations. And at some point, we notice we've seen this before. So maybe we want to optimize it. And we start tracing. what this means is we record every instruction that is executed from now on. So first, we do this if, and we record that, we compared if n0 is larger than or equal to 0, and we remember that we have to check that again. And then we might push to the stack, which is represented as a singly linked list allocated on the heap. So we allocate some stuff. Then we reach this effect operation. And to execute this effect operation, we first check what is the current prompt. And it depends on which kind of effect handler we are implementing, how we do that. But then we search the stack for this prompt, and we capture this part of the stack and put it aside into some register or variable. And then we just jump to the corresponding handler body. So we continue execution here, and we might do this again, do some instructions, capture another stack because we do another effect operation. And at some point, now we push this +1 frame, and we are at a resume. So we want to resume where we were when this effect handler was called. To do this, we take the stack that's on the side, push it back onto our stack, so this stack segment, and just return the value that we are resuming with. In this case, unit, so not too important. Then that's another resume. Again, we push another stack. We go back in here, and then we are at the recursive call, and we end up back here. Now, this is where we started in the program when we started tracing, which means we can now insert a jump to the beginning of this trace, and we have a specialized code for this specific execution. We could compile that and execute that, but first we want to optimize a bit, so we do some standard optimizations like allocation removal, some constant propagation. Also, we're hoisting some stuff out of the loop by considering mostly the later iterations, and we end up with only this optimized code. So there is 2 guards for the loop, which would probably be merged, but it's instructive to leave them separate here. And we have those 3 instructions, which push this +1 frame and reconstruct the outer stack structure. So this is still left, but at least nothing else. And of course, the loop counter that we still need to keep track of. So in principle, this seems to work out nicely, and we didn't have to do much to optimize this away. Now, how does this work in practice? Does this actually make our effect handler programs fast? And if you remember the slide earlier, then we had some research questions to answer there. And first was, how does this compare with existing ahead-of-time optimizing compilers? And this is a heat map of kind of the speed up. So when you see a green field, this means this is the fastest implementation that we've measured, and red means it's not that fast. And what we see is mostly we are pretty competitive with existing ahead-of-time implementations. Sometimes one of the chits is much faster than the other ones, but usually we are quite competitive. The other question is, when does this work well and when doesn't it? When does this work well is mostly, for example, the cases where the ahead-of-time compilers have a harder time to do this. And the generator example is kind of tailor-made for that. And you see this also in the result. Because there, the continuation is only used linearly. We only ever resume once, but we can't see that from the program code, at least not directly. And there we are definitely fast. Now, where doesn't it work as well? That's the case where we have multiple resumptions. If you remember, we are tracing through the concrete execution, and if we have multiple resumptions, so we use multi-shot effect handlers, then this results in a very complex control flow, at least potentially. And if it does, then sometimes we end up generating tens of traces, compiling them, and we're not that fast anymore. And this is also in part a known problem of tracing JITs. We have tailed application. We recompile this mostly same code again because we have a join point. So that's it. There's still tons of stuff in the paper. So we have, of course, a description of our bytecode language, which we skipped over in this talk and the translation to it. We have the answers to the other research questions, for example, by an appellation study for the additional optimizations we implemented, some more in-depth analysis of all of the evaluation, and baseline benchmarks, which I didn't show here, which, for example, also show that we can beat, for example, V8 for benchmarks which use control effects. We're roughly comparable to PyPy for baseline. So with that, thank you for your attention, and if you have any questions.
Questions?
Hello. Thank you for a very interesting talk. So could you elaborate how to handle effects in meta-tracing compilation again?
So what we do is, maybe I'm best going back to this slide, if it works. No, okay. Then that way. What we do is we have kind of a two-level linked list structure here, which means that, and that's also what you see in the trace, mostly when we're capturing the stack, we only ever have to reconstruct the outer structure, and we only have to traverse that. And because it's a singly linked list and it's immutable, we don't have to copy the stack around. We just move it around. And in the cases where it works well, we also don't necessarily need to allocate those stack frames because the tracing JIT can reason well over those immutable objects that we just looked at.
Cool, thank you.
Does that answer? Yeah.
Hi, Max New, University of Michigan. So the benchmarking, basically what it shows is what you said, that for one-shot continuations, basically the JIT compiler can figure out that can compile them more efficiently than the ahead-of-time compilation, because the ahead-of-time compilation doesn't know that they're one-shot continuations. Is that right?
Depends. Of course, for the cases where the ahead-of-time compilation can figure that out, there's not a big difference in performance.
Okay, yeah, so that's what I'm asking, actually.
Yeah.
So in these other implementations, do they have good analyses that do try to figure out that they're one-shot and compile them more efficiently, and you're still beating them? That's
for some of those cases.
Okay.
Yeah.
Okay, yeah, because that's what I want to know. Is it, should we really be focusing on making that analysis much better, or is it just completely? Are there ones where it's completely infeasible, where in real programs to discover statically?
I don't know actually if they are figuring it out. It doesn't seem so for the generator benchmark, at least, because what happens there is the continuation is stored away in some stream object, and then in some later execution it's then resumed. So it's non-trivial that this is only resumed once, but you could maybe figure it out. I assume there's some analysis. But there are also cases, and I don't think I have a benchmark for them, where you, for example, might resume multiple times, but you happen to not do that.
Okay, thank you.
Yep.
Actually, the same question. So.
Okay.
We can still have short time to accept.
Okay, the example that you showed, this uses linear stack space. Because you keep pushing these 1+s. Is that essential to
no.
this? Okay, good.
This is mostly to show that, oh yeah, we can actually support non-tail resumptions, and to kind of showcase this case that, oh, there's still some allocations left over. Of course, in a real implementation, I would just increment a counter in this case.
Okay, thank you.
Yeah.
Okay, thank you very much. And this is the end of the session, so let's thank again.